Hi, I'm Tyler Lawson, and we are Truss-In-Us, the design team for Dr. Muller's Engineering 220-002 class. With me are my partners Walker Thurmon, Cartez Jack, and Kelsey Phelan. In our project, we were trying to make a truss with the best load-to-weight ratio. With this, we were supplied with a tempered hardboard sheet with dimensions 36 inches by 1/8 inches by 24 inches. And we had to create our own individual members from this sheet. The constraints for our project, it had to span a 32-inch gap with the load applied at a joint 14 inches from one end, and it had to be no greater than 10 inches. After our design, we predicted that it would fail at 292 pounds at one of the compression members. However, it actually failed with 148 pounds, and we had a ratio of 66.36 pounds to weight, load to weight. For our objectives, it had to span the 32-inch gap, and it had to be loaded at a joint. It also had to be fastened 14 inches from one end of the truss. For our project, we could only use machine screws and glue. Also, our nuts couldn't exceed 1 inch. Members in compression had to be short as possible, that way we could get the lowest moment of inertia, and the best design had to have the highest load to weight ratio. As you can see in our pictures, we had to sand each member before the gluing process. That made sure that there was no trash or debris and the glue stuck together perfectly. We used liquid nails as the adhesive so that because we thought this would be the strongest glue and with the less weight.
For the material properties, the modulus of elasticity for the sheet of our tempered hardboard was about 700 KSI. However, when it was bonded, we had it at about 500 KSI. The tempered hardboard, it had like a brownish, tannish outward appearance that was kind of darkened due to it being tempered. But when we sanded that, it turned into a lighter brown material. The ultimate stress for the tempered hardboard that we looked up was about 130 PSI. Overall, the material was pretty darn brittle, and it would fracture very easily. So the values for our tempered hardboard were given in class, and we did so accordingly. During the fabrication process, we decided to create square beams, and the reason we did this was because we wanted to kind of prevent buckling and torsion of our truss as a whole. So when we put our truss together, we put the square beams for those that were in compression and two-fold double ply the tension members, where we bonded them in the middle along the neutral axis. That way we could have the best performance of our truss. We had two different design alternatives. For our first design alternative, we didn't go with it because it would require us to use small members, which would result in a smaller moment of inertia and ultimately a smaller stress. And for our second one, we almost chose this, but the load of our members were rather high, and therefore we didn't want to go with it because it would fail a whole lot sooner. For our calculations, we measured the length of each member, and we determined the area and found the moment of inertia, and along with that we had to designate which ones were in tension or compression, and therefore knowing that, it was how we built it into the box beam or the tension members. So then we calculated our force. We summed up moments, summed up forces, and found a force in each member, and found the axial stress, used the predicted buckling, found our tensile factor of safety and our buckling load factor of safety. Along with that, we found our shear stress and our screw factor of safety and our tensile hole factor of safety. And overall, this was our design calculation. The predicted failure mode, well, for that, our failure load, we predicted to be about 250 pounds, assuming that probably it was going to be BC that would fail. But actually, we held 148 pounds, and it was member AB that failed in tensile. Our truss failed because the load in the member AB exceeded the maximum load for the normal tensile strength, therefore the beam coming apart. Going forward, we could use I-beams to reduce the overall weight because the square beams were heavier and unnecessary in that respect, but easier to put together. And maybe we could have sanded off the excess glue and that would reduce the weight, or cut off the excess bolt, and that would reduce the weight as well. Liquid nails may not be the best fabrication avenue due to it being really messy. So maybe another glue type would be adequate. So for the student suggestions, maybe for the tempered hardboard, we had difficulty with the material properties and finding out different characteristics that would play into our equations to do our analysis of the truss. That would be helpful for students in the future in the class. And maybe a better seating method for when the bar comes down on top. We have our truss that comes up to a point, but maybe like a PVC seating method that the bar could fit in appropriately and the truss could be fully tested.
And that is our project. Thank you for watching. Following this is our references for all of our sources and appendices showing how we came out to our calculations. Again, thank you for watching.